Hello everybody. In the last class we discussed fundamentals of Boolean algebra. So, we discussed basic postulates, Huntington postulates we discussed, and some basic theorems, and we saw proof of those theorems from many of them and how to do it from the basic postulates. Today we shall discuss how to convert a Boolean function to corresponding truth table, and then we shall see how to realize a Boolean function using logic gates, and we shall see that algebraic simplification using Boolean algebra is useful for efficient implementation, and we shall also have a look at Shanon's expansion theorem. So, the Boolean function, some of the function that we have already familiarized with. So, let us take one or two of them. One is a two variable function. So, f x y is equal to x plus x prime y. Okay. So, that is x ANDed with x prime complement of x, x ORed with complement of x ANDed with y, right. So, this is we already have seen. So, if you want to get the corresponding truth table, what we do for this x y variable, we substitute 0 and 0, like over here what you see, then it becomes 0 plus 0 prime. So, this is 0 standing for x, and this is 0 prime, that is substituted x value, and then y is also 0. So, this 0 remains 0 and this 0 prime becomes 1 over here, and this 0 remains 0, right. So, this 1 ANDed with 0 is 0. So, 0 plus 0 is 0. So, this way we get one particular row of the truth table, which we see over here filled up. So, then the other option is x and y can take value 0 and 1. So, this is that option, and then you substitute and go on putting the values, and from the AND and OR operation we get 1 1 1 for the remaining 3 possibilities, and that way you can come up with the truth table. Okay. So, for a 3 variable case, this was where we had seen that product terms are summed finally. Here the sum terms, this is a sum term, this is also a sum term with which we are taking an AND. So, there is a product term that is finally formed. So, there also we follow the similar thing. This is a 3 variable problem. So, we shall be substituting x, y, z, different combinations of them. So, we start with say 0, 0 and 0. So, x and y both are 0. So, we put those values. So, 0 or 0 becomes 0 over here. Then x and z, they are 0. So, this is 0. So, we substitute those values, 0 or 0 is also 0. These two are ANDed, we get 0. Okay. So, this completes the first row of this particular truth table. So, then 0 0 1 another possibility. So, this particular row. So, again we substitute and we get 0 from 0 plus 0 x plus y, and 0 plus 1 we get 1 from x plus z, and 0 ANDed with 1 is 0. So, this is the second row that we get, and that we get all the different rows and complete the truth table. Okay, this is a very simple approach. Given any function of any number of variables, you know that the number of rows in that truth table will be 2 to the power n if n variables are there, and we shall go on substituting each values of the combination and work out the AND and OR operation and complement operation, and then finally we will get the different entries. Now, if we want to implement a Boolean function, any given Boolean function, we want to implement it using hardware. So, these logic gates are there. So, each of these logic operation, each of the Boolean operation that we do in the case of a Boolean function like this, right. So, for that a corresponding logic gate is there. So, x prime is required, complement of x is required. So, for that we have got NOT gate. So, we shall put a NOT gate, x is input at it and the output is x prime. It is very easy to get. So, this is ANDed with y, right. So, we will put a 2 input AND gate. So, there are 2 inputs to this AND operation. So, one is x prime, another is y. So, this AND gate output is x prime y, and this x prime y is ANDed with ORed with x. So, we shall put 2 input OR gate, because there are 2 inputs to this OR operation. So, this is the 2 input OR gate, and final output we get this way. So, every this Boolean operation that we do in the Boolean expression, there is a corresponding logic gate, we convert it to that and we get the corresponding circuit made. Similarly, the other relation that we had seen, so this is x plus y ANDed with x plus z. So, to achieve x plus y, we need a 2 input OR gate. Okay. This is OR operation. To achieve x plus z, we need a 2 input OR gate, that is another this is a OR operation, and finally, these two are getting ANDed, these two are getting ANDed over here. So, for these 2 such input are required for this 2 input AND gate, and finally, at this place we get x plus y ANDed with y plus z. Okay. So, we can just simply follow the Boolean any given Boolean expression operation by operation with the operands that are there. If it is a there are 2 operands, so 2 input gates will be required, 3 operands, 3 input gates will be required, and finally, the whole expression can be arrived in the form of digital circuit implementation. Remember, in this case we are not talking about the propagation delay, power consumption and all those things, it is just simple implementation of the Boolean expression. Right. Now, while we talk about this implementation, in the previous case we did not bother about those factors that can affect the realization, but in practical cases you see that amount of power you consume, amount of power the circuit consumes, the fan in, how many input can be there, fan out, how many output can be there, propagation delays, if number of stages get becomes very much. So, many such issues would be there, and we will always look for a efficient implementation, and in efficient implementation we shall try to reduce, we try to have a most simplified form of representation as much as possible. So, in that case the Boolean algebra that we have the fundamentals which we discussed before can be of very useful, I mean very important. So, the previous realization that we talked about, the previous one, that x plus x prime y, we have noted that it requires one NOT gate, this NOT operation here, one 2 input AND gate for this operation, and one 2 input OR gate for this final operation. Okay. This was what was required if we go for direct implementation just following the Boolean expression. But if we apply adsorption theorem, we know the same input output combination, the truth table, the relationship that we have seen will be available just by equivalent expression which is x plus y, right, that is from the basic theorem. So, this x plus y, if we implement, whatever we get is we get exactly the same by implementing x plus x prime y. So, it makes sense that we go for this implementation than this one. So, in that case we just need one 2 input OR gate as you have seen. And in the other example, so this x plus y ANDed with x plus z. So, from distributive law, the basic postulate, we know that this is x plus y z, and if we want to implement it, we need one 2 input AND gate over here to realize y z as you have seen, and one 2 input OR gate to realize x plus y z as it is there. And earlier it was for this case one 2 input OR, one 2 input OR. So, that is 2 2 input OR and one 2 input AND gate. So, that was the requirement, and in this case one 2 input AND and one 2 input OR. So, by using Boolean algebra, by simplifying the relationship, we see that the hardware requirement is reduced, and we have associated benefit in terms of different performance metric. So, that was a very simple example. There can be more complex relationship arrived at by examining a particular problem which is given in the form of an English statement, and when we try to convert it just by following the statement, maybe a complex relationship like this one may arrive at. This is just an example. See, this kind of relationship you are getting. So, we can go for direct implementation of this, the way we have just seen that how a Boolean expression can be realized in the form of hardware. So, we can have a NOT gate to realize C prime, then another NOT gate to realize A prime from A, then a 3 input AND gate to realize A, B, C. Then this can be ORed with C prime, a 2 input OR gate, and so on and so forth, and ultimately we can arrive at the final circuit, which is which will provide you a truth table, these 8 rows and the corresponding columns, the output function. So, the same truth table we can get if we go for a simplification process, and whatever circuit finally arrived at, if we just go for implementation of that. Okay. So, that is what is the usefulness of this simplification process. And if you try to do that in this case by following the the postulates and the basic theorems that we had discussed before in the last class, then we can see just a few steps. Let us have a look. This A, when you are ending with A prime, this particular thing. So, you get this one, the rest of the thing remains same. So, A prime is gives you a 0. So, you are left with AC only. So, this is the AC. So, from here and rest of the terms are as it was. So, then again you do a AND operation of AC, A prime, B, AC and C, right. So, this A and A prime again will give you a 0, and what you are left with is only A, C. So, that is the AC, and then the rest of the term. Then again you go for ending of this. So, AC and with A prime, B, C, and then you get AC, C prime. So, this A and A prime will give you 0, C and C prime will give you a 0. So, 0 plus 0 is 0. So, it is as good as the output Y you directly connect to logic low. Whatever you get is the same as doing all the different circuit operation, effectively it remains the same. Okay. So, that is the equivalence that we are talking about. And also occasionally one gives the identity to be proved that this is the left hand side, so that this is equal to 0. I mean, this is equal to binary 0 at the end. So, there also you can find these algebraic simplification comes of use. So, another example we can see where we use the De Morgan's theorem. So, here in this expression, this we have to simplify and then implement. We can go for again, as I said, direct implementation following the equation, but that may be more complex and not economical. So, here in this expression we see that the whole expression, there is a prime over there. So, we can apply Boolean De Morgan's theorem over here. So, this becomes A prime again A prime double prime actually. So, this is A and then B prime plus C prime, the whole thing becomes a prime, okay, because this was a NAND operation. So, this is the way we are getting it. Then this A is remaining. So, B prime plus C prime, this is again a complement. So, another De Morgan's theorem. So, this is a NOT operation. So, you can get B prime double prime and C double prime. So, this becomes BC. Okay. So, this expression then becomes A plus B ANDed with A plus BC, and this was what it was. So, if you just get the product of this, then this is AA, ABC, AB plus BBC. So, this is the corresponding term over here, and if you take A out, then 1 plus rest of the term, and we know 1 from the null theorem, if 1 is there, the rest of the terms is of no use. So, from this you have A, and this BC was there. So, this is your BC and this is the other term. Okay. So, this again you can just take into consideration A and A prime B plus C. So, in this you can use the adsorption theorem. So, there A plus B plus C is there and this is your BC. So, again you can take C out and 1 plus B, again using the null theorem you get from this only C, because 1 or B is 1 only. So, final expression is A plus B plus C. So, what you require in this case is only, earlier it was just connected to ground, here you need only a 3 input OR gate, right, and you can realize the same expression, clear. Okay. So, that is what we would do if so required before implementing any Boolean expression. We shall see whether it can be further simplified. Now, Shanon's expansion theorem is something which you would like to take note of. It has got many different uses. So, what Shannon's expansion theorem is says is very interesting. So, given any function of n variables, okay, we shall see examples of smaller number, 2 variables, 3 variables and all. Any expression of n variables, one of the variable may be taken out. For example, here x1, it could have been any other variable. So, this variable, when you take it out like this, x1 prime, and rest of the function, wherever x1 is present, you put 0, okay? And then whatever result you get, you AND it with x1 prime, and then you take x1 out, and for wherever x1 is present, you place 1, and then whatever you get, you just OR it, sum it up, then you get an equivalent relationship. Okay? This is what Shannon's expansion theorem says, right? And the proof is simple. In the left hand side, if you place x1 is equal to 0, then this is only 0 term is there, and in the right hand side, when you place x1 is equal to 0, so 0 prime is 1. So, this one, the 1 ended with this term. So, this term will be remaining. So, and in the other term, 0 ended with rest of the thing is 0. So, you will be left with this one only, and left hand side you have already substituted 0 over here. So, left hand side and right hand side is matching. Okay. Similarly, if you put x1 is equal to 1, you will get the other term. Okay. So, if x1 is 0 and if x1 is 1, then these are the two cases and they are getting summed up, and you get the final relationship, final term for the function in hand. Okay. And we can look at a 2 variable example, how it works it out. So, this f x y x plus x prime y, we are already familiar. So, if we are taking out x, right, if you are taking out x, and we would like to write it in this form. So, x prime f 0 y plus x f 1 y, right. It is a 2 variable problem. So, basically x1 is your x and x2 is your y, that is the way you are doing it. So, we have to calculate f 0 y and f 1 y. How will you do that? So, in the expression we shall substitute in place of x 0. So, if you substitute, then 0 plus 0 prime y. So, 0 plus 0 that is 1 prime y, 1 ended with y. So, this is y, right, f 0 y is y, and f 1 y is, you substitute in place of x 1. So, 1 plus 1 prime y. So, 1 ended with anything is 1. So, this is your f 1 y. So, this f 1 y is your 1 and f 0 y is your y. So, that way x prime y plus x, and you get back what you had seen, x plus x prime y. Okay. So, this will be true for any other example. This is a small example, but this holds, and its dual form. Okay. So, in the dual form, we know that it is these AND is replaced with OR, and OR is replaced with AND. So, in this case, this is the AND operation over here. So, this AND operation is replaced with OR, and this was the OR operation. This is replaced with AND. This was a AND operation over here. Okay. So, this is replaced with OR. Okay. So, it was sum of 2 product terms. This becomes product, final product of 2 sum terms. So, this is the dual form representation of Shannon's expansion theorem. Okay. Now, this can be useful in simplification problem as well, right. So, we take one example. So, this is a 5 variable problem where the right hand side looks something like this, and if we want to apply Shanon's expansion theorem, one variable we want to take out. So, we would generally look for the variable which is present in almost all the terms that you see in the expression. So, here we see that A is present in all the different individual terms. So, it makes sense that we take A out. Okay. So, if you take A out, so then we have to get two relationship, one is F0 B C D E and another is F1 B C D E, and then we shall end it with A bar F0 B C D E and A F1 B C D E. Okay. So, this is the Shannon's expansion theorem that we shall be using for taking A out. We could have taken any other variable out, B also. In that case, F A0 B C D E, F A1 B C D E, that would have been the case, and here the relationship would have been B bar F A0 B C D E, B ended with F A1 B C D E. So, that is the way you would have written the expression. So, once you take A out, then what do you see? F0 B C D E, this expression, how will you get? So, if you substitute, this is your 0, this is 0 complement ended with B, and this is 0 ended with the rest of the things. And whenever this is 0, so in the OR gate it does not contribute in any way. It is 0, so it is contributing in any way means it is dependent on other inputs of the OR gate, and this is ended with 0 means this generates a 0. So, basically you have got 0 plus 0 prime is 1 ended with B plus 0. So, basically you get 0 or B or 0. So, ultimately the result is B. Okay. So, F0 BCD is your B, and F1 BCD what it is? So, this is 1 plus 1 bar B plus 1 rest of the terms. Okay. And we know anything ORed with 1 is 1 only from the null theorem. So, this is 1, this is straightforward. Okay. So, we have got these two terms. Now, we just need to combine using the Shannon's expansion theorem. So, A bar is ended with B, this particular term is B only, and A ended with this term which is 1. So, A plus A bar B, that is what you get, and after that you can use adsorption theorem. So, this is A plus B. So, from this to this is your adsorption theorem. Okay. So, you get A plus B. So, this is the simplified version of it, and we could have taken other postulates and basic theorems also to simplify it, but we see that Shannon's expansion theorem can also be useful in such a cases. Okay. So, finally, we look at some other use of Shannon's expansion theorem. So, this was our the basic Shannon's expansion theorem. So, where x1 was taken out, right, it is clear. So, in this particular function, there are x2 to xn variable. So, this again can be expanded for another variable, and if we choose it to be x2, so this one we can write as x2 prime, this is already 0. So, we do not do anything with that. So, x2 is 0 because x2 prime has been taken out, okay, is the ending term, and rest of the terms remaining same, plus this one. This whole term is this one plus x2 f 0 in place of x2, since x2 has been taken out, this is 1, x3 and rest of the terms, clear. So, this is for this one, and for the other one we can have a similar expansion with x2. So, basically we are having x1 prime outside and inside x2 prime being considered. Similarly, x1 x2 prime and x2 over here, and x1 outside and x2 prime and x2 over here. And the corresponding terms here are f00 and rest of the terms, f01 rest of the terms, f10 rest of the terms, and f11 rest of the terms. Okay. Then we can go ahead with further such expansion of this particular term, one such term. So, x3 can be taken out. Okay. So, the first term will be f00 and second term will be f001 and all. So, that way what is known as nesting is possible using Shanon's expansion theorem. Okay. So, you can go on doing it, and it has got certain use which we shall discuss later in some of the later classes. Okay. So, here you see how it actually works out for a two variable problem. So, for a two variable problem, so say x y is there. So, x prime has been taken out, so f0 y and f1 y. So, these are the two terms. So, this y is now you are taking out. So, f00, f01, right, and then x, f10 and f11. And then if you just take the y prime outside the parenthesis bracket, so x prime y prime f00, x prime y f01, x y prime f10 and x y f11. Okay. That is how what we get by expanding it to this level. And for an example like this, the one we had seen before, x fxy is x plus x prime y. So, we have seen we formed the truth table f00, f01 and so on and so forth. So, we have seen that f00 is 0, f01 is 1 and f10 is 1 and f11 is 1. We have already seen that, isn't it? So, these corresponding terms we shall just end it up from here. We shall use these f00 terms. So, x prime y prime, so x prime y prime ended with f00. So, f00 is your 0. Then x prime y is ended with f01. So, f01 is, we have already seen f01 as 1. So, this is your 1. Okay. So, f xy is ended with f11. Okay. So, that is your the final 1 over here. So, all the terms that you can see are coming here. So, this is being 0, this term is not there, and rest of the terms x prime y, x y prime and x y, that would be there in the final expression. Okay, when you expand it to that level. Okay, you can further simplify it. We are not talking about simplification over here. We are just saying that this is the way you can represent up to this level. You can, if you go on expanding it to that level, and then if you just this x prime y, and you can take x out and y plus y prime, this from complement postulate, complementarity, we can see that x prime y and this is 1. So, this x plus x prime y, we can get back this one, that is the simplification process. But if you get all the terms in terms of individual variables, these are the 3 terms that you will get. So, you can see in the truth table, this 1 is there in 3 cases, right, and there are 3 such terms where all the variables expanded to the in the maximum possible way. That is what we see. Okay. This has got its use in our subsequent discussion. We shall begin our next lecture, next class, from where we leave here. So, to conclude, what we have seen today in this particular class is we can obtain a function output by substituting variables with possible binary, all possible binary combinations, and we can get the truth table out of it. And this any Boolean function given to us, we can realize it using logic gates by getting those logic gates which corresponds to a specific logic operation. And algebraic manipulation helps to get a simplified implement a Boolean expression. Boolean algebra comes very handy in that, and Shanon's expansion theorem and its nested version is useful in algebraic manipulation of a Boolean function. Okay. Thank you.